nutrition in the southern cone. Thank you very much, Gaston. Thank you, everybody. Thank you for being here with us in this last session this morning. And also like to thank Aapresid and the organizing committee for inviting us and for inviting Rob Mikkelsen to talk about this connection between crop nutrition and the environment. I believe that the previous conference by Dr. Lada was very interesting because he introduced the subject matter of the environment. So now I give the floor to Dr. Mikkelsen. So before introducing Dr. Mikkelsen, I'd like to remind you that you may send your questions to the phone number that appears on the screen, and if there is time, the questions will be answered after the presentation. Dr. Mikkelsen has a doctor's degree in soils granted by California University. He is the Director of Communications of the International Institute of Plants. He is an international expert in the management of nutrients, and he is also the author of several books. So let's give the floor to Dr. Mikkelsen, who will talk about connecting crop nutrition and the environment.
Thank you very much. It's a pleasure to be at the Congress and to participate in such a fine organization. I have really learned a lot and learning more about the agriculture of Argentina. I was asked today to talk about some of the environmental issues that we're dealing with crop nutrition. There's many problems throughout the world that we're working on, and it requires good agronomy and good management by people like you to solve some of these issues. So I'll talk about some of the issues that we're dealing with in North America, and I have a feeling that some of these issues will be coming to Argentina as well, if you're not dealing with them. Dr. Lada talked about this issue. We won't spend much time, but the link between food production and fertilizer is very strong. They estimate that over half of the world's food is supported by fertilizer. Or in other words, if we did not use fertilizer, food supply would be cut by at least 50%. So fertilizers are very important, but we need to manage them in a very effective way. I'll give you some examples of how fertilizer can be managed properly, and then places where fertilizer needs improvement still. As we heard through the previous talk very nicely, that nitrogen use efficiency is usually low, often 30 or 40%. For some crops, it may get as high as 70%. For maize, for some crops I deal with, it can be as high as 80, but that is quite rare. So usually, nitrogen use efficiency is low. And then the nitrogen that is removed from the crop in the harvest is even lower. So uptake is low, and then removal is even lower. Also talk about phosphorus recovery, phosphorus efficiency. In the first year is very low, maybe 20%, 25%. But if we look at many years of phosphorus efficiency can be very high. So it depends on how you measure some of these things, and if you're looking at a very short term or looking at a long term. So the definitions can change. So we've heard a lot about this already. Dr. Lada discussed this, and this is some of his data as well. But soil nutrient depletion is a major issue. Our nutrient budgets are negative. We are removing more nutrients than we're applying back to the soil again. And that is not sustainable. We can do that for 10 years, 20 years, 30 years, but at some point, the nutrients are depleted and we need to start putting fertilizer back. But we need to be smart about doing it and do it in a way that is environmentally sustainable. So Dr. Lada mentioned that about 4% of nitrogen comes from soil depletion worldwide. We saw some figures yesterday from Dr. Garcia, and maybe he will talk more about this. But nutrient depletion in Argentina is very severe. Nitrogen, phosphorus, potassium, sulfur. All these nutrients are being depleted from the soils in Argentina. So although grain yields have increased for many years, we are mining the nutrients from the field. So let's just talk for a few minutes. We'll talk about nitrogen and some of the problems, and then we'll talk about phosphorus and some of the management problems related to that. So you're familiar with this, the different ways that nitrogen can be lost from fields. Mineralization provides nitrogen or nitrate that can be lost or taken up by the plant. We'll talk briefly about ammonia volatilization, and Dr. Lara spoke about that. Nitrogen leaching, which is a big problem in my country. We are contaminating our groundwater. Denitrification also is becoming a large problem when we look at greenhouse gases. So there's not one solution to managing nitrogen. You have to think of many different pathways and decide how you can address all of these things at once. So we'll talk briefly about ammonia volatilization, and even that is difficult to manage properly. As you know, ammonia volatilization occurs more rapidly when the pH is elevated, when you use urea, when the urea is applied on the surface, such as with conservation agriculture, with crop residues, in warm and moist conditions, and more ammonia loss with sandy soils. But looking at this list, many of these things are exactly where plants grow best. Surface placement, residues, warm, moist. So many of the conditions that are good for growing crops are also good for losing nitrogen, both through denitrification, ammonia volatilization, and leaching. So we're always struggling with getting the most nitrogen in the plant without losing it in these conditions. And additionally, most ammonia losses come from animal manure in many places. Often it's 25% or more of the nitrogen that's used from animal manure will be lost as a gas. But even from fertilizer, it can be very significant. Nitrous oxide has become a major issue in the last 10 or 20 years because it is a major greenhouse gas. You know that it's one of the major greenhouse gases along with carbon dioxide and methane. Nitrous oxide is a very powerful greenhouse gas, almost 300 times more powerful than CO2 for each molecule. So for each molecule of nitrous oxide we can remove from the atmosphere, it's like removing 300 molecules of CO2. And we can measure how it has increased over the years to over 330 parts per billion now. So it is increasing every year, and agriculture is a major source of that. So it's very important that we manage for nitrous oxide for environmental purposes. So similar to the ammonia loss, the things that favor denitrification also often favor plant growth. Nitrate, warm, moist soils, good rainfall, good irrigation, lots of carbon. All the things that are good for plants also can stimulate denitrification. But generally, this is not so important for the farmers. It may only represent a loss of 1 or 2% of their fertilizer. But for the atmosphere, it's still very important. So there's a lot of concern for the United Nations and all the governments on how we can reduce nitrous oxide losses from fertilizers. So some of these things we can control by management practices. Some of them are not so easy to control by environmental factors. We've heard reference to the 4 R's. And the 4 R's can make a very large contribution for reducing nitrous oxide. For example, changing the fertilizer type can reduce nitrous oxide. Changing the rate is a very important factor for reducing nitrous oxide. How you place the fertilizer is important, and how you apply it during the time of the growing season is important. So we can change many of these factors that will reduce nitrous oxide evolution and have a major benefit for the environment. But these things are very complicated, but we can improve it with nitrogen fertilizer management. Just for an example from the United States, nitrous oxide is about 5% of the greenhouse gas emissions in the United States, and nitrous oxide emissions are going down while crop production is going up. So that's a very good trend. We want nitrous oxide to continue to go down while we produce more food. But still, agriculture in the United States produces almost 9% of the greenhouse gases But if you actually, agriculture in general, that includes transportation, food production, processing, in that 8.7%. But actually the processes in the field are much lower. It's about 3.8% of greenhouse gas emissions. But agriculture is responsible for many of the nitrous oxide emissions. So that's where we're focusing much of our efforts. Looking at the greenhouse gas emissions from the fertilizer industry in general, just to give you a global sense, manufacturing of fertilizer is important for greenhouse gas emissions. The distribution, not so important, but the fertilizer use in the field, they estimate about 1.5% of all greenhouse gases come from fertilizer applied to the field. So these are important for the global greenhouse gas emissions. So let me give you some examples of what happens when we don't use nitrogen properly. I wanted to give you the example using the Mississippi River basin in the United States. And you see the colored area where the river drains into the Gulf of Mexico. There's a report that was released today by the U.S. government that said the extent of that polluted zone, the hypoxic zone in the Gulf of Mexico, is the largest in 2017 that it has ever been. This year's the greatest, or the worst. And some of that is coming from fertilizer. So the problem we were hoping was getting better, but it continues to get worse. Just to give you some idea about this Mississippi River basin, it's very large in the United States. It drains over 41% of the United States and drains 21 of our 48 states there. Fourth longest river. So Mississippi River is very large, very important in the United States. Not only is it very large, most of the fertilizer in the United States is used in this Mississippi River basin. 88% of all the nitrogen is used in this area, 92% of the phosphate, and 86% of the potash used in this very fertile, very important agricultural region. So because so much fertilizer is there, that's where we're focusing on how to improve fertilizer management so it reduces the nutrient loss to the Gulf of Mexico. So looking at where these nutrients come from that end up in the Gulf of Mexico, they estimate that about 41% of the nitrogen that goes through the river comes from fertilizer. It's the largest contributor of nitrogen to the river. It's not the only one. The other ones are also important. But the fertilizer is one that we can manage and try to improve. Phosphorus is also very important. We look at phosphorus losses in the Mississippi River, and about 27% of the phosphorus that goes to the river estimated comes from fertilizer. So for phosphorus, manure is very important also. It's an area of a lot of animals, a lot of pigs, chickens, and cattle. So we need to improve the manure management and the fertilizer management in these areas. But when you look at the amount of nutrient that is lost to the Gulf of Mexico, kilograms per square kilometer per year, some of these numbers are very high. How much of the dissolved nutrients are coming to the river? Over 500 to 1,000 kilograms per square kilometer every year. So there is a lot of room for improvement, for better crop management. And it's great to hear the conservation tillage, the conservation agriculture talks that are presented here. I think in many ways, Argentina is far ahead of many of our farmers in keeping the residue on the soil, keeping erosion down, keeping the runoff minimized. So there's some simple practices that we can implement to improve these high losses. So not only is it an environmental loss, but it's a very important economic loss. When you look at the amount of nitrogen and phosphate that has been lost to the river in the last 35 years, many billions of US dollars applied to the field and then gone. So this is the one that gets the farmer's attention. They're going, ooh, I don't want to lose my fertilizer. So we have a lot of work to do still. Another issue that we're dealing with for nitrogen management is for ammonia. And so the farmers are often concerned that ammonia is lost from their fields, but there are also environmental issues related to ammonia. This is an area near my home on days when ammonia is high. So it's very hazy. The nitrogen is coming down in the rainfall, fertilizing the forest, fertilizing the water. People with bad lungs, with asthma or respiratory problems, they find it difficult to breathe when there's high ammonia. So there's also pressure to reduce ammonia loss. So this picture shows the same place on a clear day compared to a day where there's high ammonia in the atmosphere. This is the valley where I live nearby, and this is the red is high ammonia with the green, and then different concentrations of ammonia in the atmosphere. And partly this is because there's many animals in this area, and also there's many mountains and no wind, so the ammonia accumulates, is trapped, and for many days it just grows and grows in concentration. So for air quality, for people, for many reasons, we're trying to reduce ammonia volatilization and improve the air quality. So an example from California, they decided we need to keep track, like Dr. Lado was saying, of the nitrogen balance. It's like a big pool or a big bathtub. We want to know what goes into the bathtub and what comes out of the bathtub. If it goes in faster than it comes out, then it will cause a problem. If it goes out too fast, then it will be mining the soil and depleting the soil. So this last year they decided we will keep a balance, and we will require every farmer to do this. So I'll show you an example. So the government said we want to do the total balance of nitrogen. And this was prompted because many of our wells are now high in nitrate. Some of the wells are used for drinking water. Some of the wells are used for irrigation. But it's primarily the ones for drinking that people are concerned about. So many of the wells are above 10 parts per million nitrogen. And this is mostly because of a history of agriculture for many years and a lot of nitrogen use. So, and in some of the valleys, it is very bad. This is a very important vegetable growing area, very near San Francisco, California. And you see, most of those wells are above the human health standard for drinking water nitrate. So they needed to set some regulations to get the farmers to lower the nitrate concentrations. And you look at how much nitrogen is being applied, looking at the loading, how much surplus nitrogen is added every year compared to removal. You can see the red areas are over 500 kilograms of extra nitrogen per hectare per year. Very high. So there's no surprise that the groundwater is also polluted with nitrate. So this forced the government of California to come to the farmers and say, you must change your practice. So what they have done is develop a nitrogen plan for all farmers that they must submit every year for every field. So they are required to say, what is my expected yield? How much nitrogen will I need for that crop? And then report their actual yield. How much did you harvest from the crop? How much nitrogen did you apply? So these are all required for the farmer. And then for the nitrogen supplied, they're also required to say how much foliar fertilizer, how much organic fertilizer, how much nitrate was in the soil, to take a soil sample and have it analyzed. Were there legumes? was the residual old organic matter. How much nitrogen came from the soil organic matter. And when the water is polluted with nitrate, how much fertilizer came in the irrigation water. And sometimes that can be 20, 30, 50 kilograms of nitrogen per hectare in the irrigation water alone. So every farmer now is required to fill this sheet and then have a certified agronomist sign this and say, yes, this plan makes sense. Yes, the plan should be in balance. So they make the plan at the beginning of the year, and then they report it at the end of the year, what they actually did. So many of the farmers were very unhappy about this, you can imagine. Say, who is the government to tell me what to do? I know my farm the best. And so many farmers are doing an excellent job. And so I think there are no penalties now, it's only reporting to the government. But I think in the years to come, they will find the farmers that have a bad balance and say, oh, you need to improve. So for now, there are no penalties, it's only reporting and for educational purposes. And for many of the crops we grow, many of the horticulture crops in particular, it is very hard to get a good nitrogen balance. Here's some example of very important economic crops where I live. So the application rates, and then what the plant takes up, and then what is actually removed from the field. So in many horticultural crops, you only take a small part of the plant and leave all the other nitrogen behind. So the nitrogen balance looks very bad. So much worse than grain crops, much worse than maize, much worse than the rice that we heard about before. So the same issue with poor nitrogen use efficiency in these crops is also true in China, where we've heard many stories about nitrogen pollution, too much fertilizer. The problems in China are also mostly with these horticultural crops, where they apply a lot of nitrogen, they are very valuable, and then they only remove the berry or the fruit. The rest of the crop is returned to the soil. So I thought it might be interesting just to look to see, there was a study done a few years ago at the nitrogen balance for entire countries. Which countries are in good balance, which countries are not so good. You see South Korea on the far left-hand side, very large nitrogen balance. So on average, they use 240 kilograms more nitrogen than they remove in the crops. They're really bad. Netherlands has a lot of animals, a lot of livestock, a lot of pigs, so their balance is also very high. And then it goes down, so the United States is not so bad compared to some countries. And then on the far right is Iceland, which has no agriculture anyway, so it's easy for them to look good. So the data is sort of old. The study was just released in 2012. So I think these numbers have come down for everyone now, but still there's a lot of room for improvement. Nitrogen balance in many places are not so good. So let's talk a little bit about phosphorus and some of the issues that we're dealing with phosphorus, and then we'll summarize by how we can make progress for both nitrogen and phosphorus in the years to come. So as agronomists, I was trained to look at the farm, but I never learned about water quality and the environment and issues related to phosphorus. But that has all changed now. It's very much related to sustainability, water quality, issues related to how to preserve, recycle, recover phosphorus. So a lot of scientific work is being done on phosphorus management now. So it's a very large issue. And when you look at the global phosphorus cycle, you think about, well, we mine the phosphorus. It may come from the United States or Morocco or Saudi Arabia, many places. We put it on the soil. We take a little bit in the food, and then after it goes to food, then we waste it, we throw it away. There's very little recovery, little recycling, very little reuse. So the phosphorus balance is very bad globally. So we count on mining more every year. put it to the soil, and then throw it away. So I think there'll be much work in the future about how do we improve phosphorus management, how do we recover it, how do we use it better. We have many hundreds of years of phosphorus remaining to be removed from the mines, from the rocks. But when you look at the large scale, only a few hundred years will go quickly. So we need to use this more sustainably and do a better job of efficiency. So one example of phosphorus that we've been dealing with is a large lake called Lake Erie, which is located on the Canada-United States border. And you can see at the left-hand top part of the lake, there's a large algae bloom where the water is green. And that is due mostly to phosphorus contamination. In 2014, the phosphorus washed into the lake and the algae started to grow. And the large city on the left-hand side of the lake had to stop bringing in water because it was so polluted. They couldn't treat it enough for drinking water. So it became a very large issue in the United States. So we've been working on where did this phosphorus come from? How can we manage it better? How do we keep it out of the lake? And the conclusion was we need to reduce phosphorus inputs into the lake. That's the most important thing. So you can see again the phosphorus in the algae blooms in the lake. So one of the problems around this lake is mostly agriculture. Back in the 1990s, we were successful at convincing these farmers to change from conventional tillage to no-till. That transition to no-till helped very much with erosion and with particulate loss. We thought the problems were finished because now instead of tilling every year, they would do no-till and put the phosphorus on the surface of the soil. We solved one problem. We didn't know that we were developing a second problem with phosphorus contamination. So we have some data from one small watershed near the lake. You see the lake, and then we'll talk about this one sub-watershed near the lake. So we've showed that dissolved reactive phosphorus, the algae use, is much larger when you broadcast the phosphorus compared to when you incorporate it. So we've been telling farmers to broadcast it, stop tilling, but we have data now to show that it's much worse. So let me show you just a couple examples from that. So one of the things we have learned just recently is that if phosphorus is in the soil, on top of the soil before rainfall, it will quickly wash off the field and into the lakes, the rivers, the streams. So the red bar shows when fertilizer is applied, and the blue bar shows rainfall or runoff. And then the black dots show phosphorus running off of the field. So if you apply fertilizer before the rainfall, you always get a large runoff of fertilizer. And that stimulates the algae to grow, and it causes more environmental problems. So you need to be telling farmers, look at the weather forecast. If it's going to rain soon, do not put fertilizer out on the field, because it will wash off quickly. The longer the phosphorus can be on top of the soil, the more reactions you have, the more absorption and precipitation, and then the less vulnerable it is to being lost in runoff. So you need to watch the weather very closely. We're also encouraging farmers maybe every 10 years or so do some incorporation to move the phosphorus into the soil a little bit. So timing is very important. And also the placement. We'll only look at the graphs on the right side for now. So the red dots show phosphorus loss in the runoff. The ones on the right show when phosphorus is incorporated, phosphorus loss in runoff is very low. But when you leave it on the surface, phosphorus loss can be very high. So again, we need to think about how we're applying the phosphorus, not always leaving it on the surface. But is there some way we can get it below the residue, get it into the soil? Or if we cannot solve this problem, then the farmers will be told, no more no-till. You'll need to go back to conventional tillage to move the phosphorus down. The things that we do for reducing phosphorus loss, much of that can be done with the 4 R's. This shows how much phosphorus loss can be reduced by using the 4 R's. This is from a paper by Dodd and Sharpley a few years ago, and a nice review. He said if you change the rate of phosphorus, you can reduce the dissolved phosphorus. If you change the time you put the phosphorus on, as I showed previously, you reduce the loss of phosphorus. If you put it in the right place, beneath the soil surface, you reduce the dissolved phosphorus, but you might increase particulate phosphorus, or the eroded phosphorus. It's interesting looking at conservation tillage. They said if you use conservation tillage, you increase dissolved phosphorus by 300% in the runoff. But you might reduce particulate loss by 96%. So, like so many things we do, there's a trade-off. We want to promote conservation tillage, but it will cause more phosphorus loss. Cause the phosphorus to go to the lake and cause the algae blooms. And the people don't like that when they can't use the lakes anymore. So always a trade-off between soluble and particulate phosphorus. One of the things we often ask people to do is think about the cropping system they're using. Where are the roots? For example, this very shallow-rooted crop, we use a lot of nitrogen on it to grow, but don't use very much. So you need to keep the nitrogen very shallow all the time. So frequent applications, just a little bit of nitrogen every time, maybe fertigation even. You need to manage it very closely. Compared to a crop that is very deep, it uses the same amount of nitrogen per year, but has a very deep rooting system that can recover much of the nitrogen that we apply. So the crop on the top, usually very low nitrogen efficiency, because the management is so difficult. The crop on the bottom, we can get 80 or 90% nitrogen recovery, nitrogen use efficiency, because the plants are very different. So think about those roots and how we manage them, because that's really the key. Dr. Lara also talked about getting the nitrogen into the plant, and it starts with the roots. As we're talking about conservation tillage and conservation agriculture, I see this often, that we develop a compacted layer. So the roots cannot penetrate either with conservation tillage or with conventional tillage, and then the nutrients continue to move down below and they're not recovered. So I think as we're talking about nutrient management, we have the 4 R's, but we also need to include the roots. Make sure they are healthy, make sure they are able to recover the nutrients that we're using. Another thing that is so important that we don't talk about sometimes is the importance of balanced nutrition. This is from some work that's been going on about 50 years. This is just from the last 20 years or so, this data. They've been growing maize in rotations, but when no fertilizer is added, the yields are low. When phosphorus is added, yields are improved. Nitrogen only, yields are improved. But you need both nitrogen and phosphorus together to get the yields we want. So this shows the yields, but the environmental results are very similar too. If you don't have nitrogen and phosphorus together, you have much more nitrate leaching from the soil, because the plants are not healthy, the roots are not going as deep as they can, and they're not as effective as using the nutrients as we would like. Another thing I think will be increasingly important is the use of precision agriculture. This is a crop that I work with, and this is from it's a 40-hectare field So we analyzed every tree to see what the yield was in 40 hectares. Very big project. Thousands, 16,000 trees. So this is the yield map of a 40-hectare field. It ranges from about 25 kilograms to about maybe 60 or 70 kilograms, all in the same field. It all receives the same fertilizer, all receives the same water, all receives the same management. But the yield potential is very different. So we know if we fertilize this for average yields, half of the field does not receive enough nutrient, half of the field receives too much nutrient. So average doesn't help us very much. We need to learn more about our soils, more about our fields, more about how the plants are working to use the nutrients appropriately. So precision agriculture will teach us a lot about how to do this, how to measure the soil properties, how to measure the good parts of the field, bad parts of the field. I think to make progress on nutrient use, we'll need to know more about precision ag. So yield, as Dr. Lara talked about, is what's driving this. Higher yields means more nitrogen in the plant. So we need to know how to measure yield, how to predict yield in different parts of the field. So to fertilize a field that is so variable is a real challenge. So just to summarize some of the things we've talked about, the challenge between food production and nutrient use is very difficult. The environmental pressures are becoming very strong, that we don't want pollution, we don't want water degradation, we don't want soil degradation, we can't have air pollution. So for agronomists to try to increase food production and environmental quality is a real challenge. For us, we have a lot of pressures. The farmers are feeling like it's a real hard thing for them to do. But I think we've talked about these 4 R's many times, but I think that is the key for making progress. To really think about, what am I doing and why am I doing this? Many of the farmers I work with, they have traditions. I always do this. My father did this even. And so if we can think about what is the right source, the right rate, the time and place, we'll make a lot of progress for meeting the environmental goals and maintaining food production and meeting the expectations of a greater society. So we have a lot of challenges ahead, but I think there's no way forward but to improve our science, improve our agronomy, and become better stewards of land and water. So I'm pleased to be with you today. I thank you for your attention, and Dr. Garcia and I hope we can answer any questions you might have. And, okay, thank you.
Le agradecemos a Rob.
Thank Rob Mikkelsen for his presentation, and now we open the Q&A session that will be moderated by Fernando Garcia. Well, first of all, we'd like to thank Dr. Mikkelsen for his excellent presentation, which has taught us a lot and has been very educational. And we have now the first question. The first question would be, how do you explain the pollution and contamination problems caused by nitrogen, which you have in the U.S., if according to the nitrogen balance, but if your nitrogen balance is positive in only 40 kilograms per hectare?
Much of it is determined by site-specific factors. So we can talk about averages, and on average, there's not a big problem. But in California, for example, nitrogen use is very high, so the pollution problems are very high. In many parts of the Mississippi River that I showed you, the nitrogen loss is not so high, but the land area is very high. And so it accumulates, and the loss is very great. So even though the balance on average is not so high, the losses can still be high for important watersheds and important places.
Creo que esta pregunta es interesante.
This next question is interesting, and it may give rise to another question or to a discussion we have in Argentina. You have seen that our balance, nutrients balance in Argentina is still negative, quite negative. But it would be really interesting for us. Well, we know there are specific areas where there are some issues already because they are using too many fertilizers. But in general terms, based on what you have learned about this week, where should we focus in order to, should we focus on monitoring, measuring our waters, rivers, soils, emissions? Or should we pay more attention to the 4 R's? Which do you think is the priority for us to care for this relationship between nutrients and environment?
Thank you for that nice question.
Muchas gracias por su pregunta.
I think all of those things are important, but you can't do everything to start. I may go back to the example of phosphorus near Lake Erie. The phosphorus balance is pretty good. So it's not out of balance, but how they're managing the phosphorus is causing the problem. So you cannot only look at balance and say, oh, the balance is bad, so it is causing problems. You need to look both at the balance and the management that's happening on the field. I think places where the nutrient deficits are very great, where you're mining the soil, you can still have pollution problems. So just because you remove more phosphorus than you apply doesn't mean that there's no environmental problems. So the management is important. But I think that nutrient balance, that budget is also important, because you will degrade your soils over time to very poor quality if you continually remove nutrients. And Africa is a great example of where nutrients have been removed for many, 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 many years, and the soils are very poor now. So you want to maintain the balance, but you want to do it in a way that you manage them so there's no problems.
There was a question before this one. Could you put it back on the screen? But I think it referred to, thank you. Do you have any experience in the use and the site-specific application of organic fertilizers?
Organic nutrients are very important, and we always recommend the farmers use those if they are available. So there's really no conflict between organic fertilizer or mineral fertilizer. But there are some site-specific technologies that are available for manure. They're not very popular now. Often the people that are growing animals just want to get the manure on the field quickly and go back and take care of the animals. So it's a challenge to get the animal producers to use the manures very well. So there is technology available, but it's not widely adopted yet.
In your presentation, you showed that in a non-till environment with phosphorus, more phosphorus was lost. Was that the case? And if so, why, even when the phosphorus was put into the ground?
The example that I showed you, phosphorus, when it's placed on the surface, dissolves quickly, and then it can be washed from the soil surface. And that, in this environment, was the largest source of phosphorus going into the lake and causing the algae blooms. When you incorporate the phosphorus into the soil, you don't have so much phosphorus running off of the soil. It's dissolved phosphorus, but it is lost as particulate phosphorus. It's attached to the soil particles that are eroded to the soil. So it's a trade-off between soluble phosphorus running off the soil or losing soil in the erosion. Both of them are bad.
Yo no recuerdo bien el dato.
I don't remember exactly the figures, but the question was actually about, we saw in the chart, phosphorus in the soil. Even on the non-till system, there was a greater phosphorus loss. I don't remember exactly the figures you had on your chart.
The phosphorus loss
phosphorus loss.
It was not phosphorus loss incorporated and no-till. No, it's not.
Vos mostraste también, me parece algo.
Also showed something interesting, and maybe you could expand on this. There is a plan whereby farmers have to report their nitrogen balance to the government. This is for California. What happens in other states? For example, in the Erie Basin area where you show those phosphorus levels, do farmers also have to report what they use there? Is there a plan for the use and management of nutrients? Are there penalties if they use more than what they put into the soil? Are there policies that will help them or assist them if they use good manufacturing practices?
In the United States, they're allowing each state to come up with regulations that are appropriate for their conditions and their cropping issues. So, for example, in California, there's a lot of irrigation and very high-value crops. So regulations in California would not be appropriate for other parts. So for now, only California the farmers are required to report to the government how much nitrogen they are using. The example of phosphorus near Lake Erie, that is a voluntary program now. They're educating the farmers, trying to help them adopt better practices, but now it's not required. But if the conditions do not improve soon, they said, we will make it mandatory. So we will give you 1 or 2 years. If you don't do it voluntarily, we will require it. So we will see. That was also the case with the Gulf of Mexico. It's voluntary programs. But every year the pollution seems to grow in the Gulf of Mexico. For 2017, it's the largest ever recorded. So I think the government will now step in and say, you must make these changes. And since the Gulf of Mexico goes through so many states, it will need to be a federal program rather than a state program.
Tenemos otra pregunta más.
Another question here. I think this question was also asked to Dr. Lerda, and this deals with nitrification inhibitors and volatilization inhibitors for ammonia, right? To what extent could they help us to improve efficiency in nitrogen use?
My answer might be different than Dr. Lada because we work in different places. He was saying for the rice situation in South Asia, he didn't think the inhibitors were so useful. We find them very useful. The urease inhibitors are very effective at reducing ammonia loss. So if you can apply the urea with an urease inhibitor, it can reduce ammonia loss to almost zero. So the farmer still needs to say, is this a good economic value for me? But they're not so expensive that it's impossible for the farmers to use. Many farmers are using them now to reduce ammonia loss. So I think it's a nice option, especially in areas where ammonia is very high, where it's a concern, and that it's a nice opportunity for the farmers to use those.
Poco la situación que nosotros también tenemos acá.
Similar to what we face here, several of those urease inhibitors have shown very good results in terms of reducing ammonia volatilization. There is a question about the California report and nitrogen balance. The state requires objective yield, actual yield, to be reported. How is this estimated, considering all the spatial and time variability that yield may have? Do you use simulation models, or is it just a farmer's opinion?
At the beginning of the season, they are required to estimate what their yields will be. And that may be based on the history or their experience or their knowledge. And then at the conclusion of the season, they need to report how much was actually harvested from that field. And they should be measuring the yield, but truthfully, no one will check it. So you can tell your yield and no one will really know. But they're supposed to measure the yield, how many tons they harvest.
I'd like to go back to the impact. You said that in the Mexican Gulf, the hypoxia area, this year you will have the largest levels ever. And there are voluntary programs for good agricultural practices that have tried to be more extensive and widely used over the last few years. When we see environmental problems, we hear people talk about legacy. We will still be inheriting these problems for many years. Can you expand on this concept of legacy?
Yes, that's a very good question. Thank you. Many of the soils that are drained by the Mississippi River are very rich in organic matter, very black, very fertile. And so anything we do to the soil will cause nitrogen to leach out of the soil. Even if there's no farming, no fertilizer, just by growing a crop, you often lose more than 10 parts per million of nitrate nitrogen to the drainage water. So it's very challenging for the farmers to reduce nitrogen loss to below the drinking water limits because of the mineralization of organic matter. So it's going to be very difficult. And for phosphorus, we have recommended to the farmers to build up the phosphorus concentrations so there will be no deficiencies. So for crop production, that's been very good. And so many places now it's time to stop the fertilizer and you can bring those down again. So you don't keep adding and building forever. But you want to measure your soil, and then when it's satisfactory, you can stop application. That will help with some of the environmental problems.
There is an interesting question, and I'd like to relate this question to some data that Rob showed in his presentation. When you talked about phosphorus in the Erie Lake Basin, you showed the effect of the application time and the time when it rains, rainfall time. So my question is there any other component there? What about the slope of those fields, of those plots? Because of the transfer to the water sources, should we consider slope as well?
That's also a very good question, Dr. Garcia. Most of the phosphorus comes off of a small part of the field. Maybe 20% of the field can account for 80% of the phosphorus loss. Some maybe the slope part or the part near the water. So things we can do. We don't have to always manage the entire field, but there are parts of the field that are very vulnerable to phosphorus loss. So that's a great point. So maybe adding a buffer strip, adding grass, moving back from the stream a little bit, many things we can do to find the places where most of the phosphorus is lost and manage that very well. So, good idea.
I asked this question because it's a question from the audience that asks about the best way to replenish phosphorus in Argentina with a no-till system. So which would be the best way? And I'd like to give my opinion about it. I'd like to answer that question myself, and I'd like to see what you think about it as well. We've discussed this several times with many of you. We've talked about the need to know the phosphorus availability in our soil. Rob was telling us that from an agronomic point of view, we want to take it up to a level where there is no phosphorus restriction, but we don't want that level to be excessive either. This is why we use soil analysis, and we insist on the importance of soil analysis. Usually we are always lagging behind. We are at the bottom and we have to go up. But if you were on a plan to replenish phosphorus, obviously you should consider those limits, which are the levels that we consider critical thresholds for the different crops. 20 ppm for wheat, 30 ppm for alfalfa, 15 for maize, 9 to 12 for sunflower and soybean. Obviously, in those plans, we try to emphasize that if we are to do anticipated broadcast application, we have worked on this with many of you. Agustin Mancini was here with us, and he worked hard on this. That anticipated broadcast phosphorus is recommended under certain circumstances where there is no slope and where there is no rainfall forecast. That is my personal opinion. Is there anything you'd like to add to this recommendation?
One of the problems we have with phosphorus in no-till is that it becomes stratified right at the very surface. So sometimes the roots are growing here, the phosphorus is at the surface. Especially where we are, the surface often dries out, and the roots cannot access the nutrients that are at the top. So we are applying phosphorus every year, but it's not getting to the roots that need it. So we don't, or maybe injected fertilizer, maybe not tillage, but at least injecting the fertilizer deeper down so you have access, the roots can find it and have the moisture to take it up as well. So, but not full tillage, but just a little bit of injection.
Yo tengo una última pregunta para Rob.
I have one last question for Rob. You talked about environmental problems with nitrogen and phosphorus. And very quickly, or very briefly, what do you think might be environmental problems in connection with potassium, sulfur? Have you seen any problems with these two nutrients?
Nitrogen and phosphorus are the ones that cause the problems with water quality generally. Potassium, there's usually an abundant supply in the environment, so it doesn't cause algae to grow, it doesn't cause any air pollution problems, so no environmental problems with potassium. The same with sulfur. When sulfate gets in the water, it's really not much of a problem. There's usually a lot of sulfate in the water already, and we want to keep sulfur dioxide out of the air. That can cause acid rain, but that's not related to agriculture. That's more related to industry. So nitrogen and phosphorus are the ones that we worry about. Potassium and sulfur, really not much of an environmental problem.
Since there are no more questions from the audience and we have to close this panel,